awak. Awak yang tu lah. Jangan lupa subscribe channel kita. Tanda sokongan. Terima kasih. Hai, Assalamualaikum. Jom kita revise sambil berehat. Sambil berehat pun kita boleh belajar tahu dengan tengok handphone. Apa tunggu lagi? Jom kita mula. Hi and hello. Dalam video kali ini kita akan tengok berkaitan dengan Induced EMF dan kita akan discuss berkaitan dengan 3 kes yang berbeza. Yang pertama iaitu berkaitan dengan coil and it is about non-rotating coil. And the second case is still about coil, but this time we will discuss about rotating coil. And the last one, the third case, we will discuss about induced EMF in a straight conductor. Okay, kita akan tengok 3 equation yang berbeza dan kita akan tengok bagaimana untuk kita tentukan direction of the induced current dalam 3 case yang berbeza ini. Jadi, jom kita mulakan dengan case yang pertama. So, let's discuss about non-rotating coil. Apa yang dimaksudkan dengan non-rotating coil? Alright, so let's look at this diagram. So here we have a magnetic field where the direction of the magnetic field indicated by cross sign is into the page. Okay, arah untuk magnetic field bagi example ini adalah into the page. And now let's say we place a coil where this coil is non-rotating coil. So based on the Faraday's law, induced EMF is equal to negative N d phi over dt. So remember from the previous video, we have discussed that when there is a change of the magnetic flux, so there is an induced EMF in a coil. Alright, so sekarang kita gantikan equation magnetic flux with BA cos theta as shown in this video. And for the first case under non-rotating coil, so let's say the angle is equal to 0. So angle apa tu? So angle equal to 0 is actually the angle between A and B. So kita dah pernah discuss dalam video sebelum ini. Okay, jadi katakanlah when A and the angle theta is constant, tidak berubah. But if the magnetic field is changing with time, so we have dB over dt ataupun kita panggil sebagai the rate change of the magnetic field, maknanya ada perubahan magnetic field with time. Okay, so bila ada perubahan magnetic field, seperti yang kita dah pernah discuss dalam video sebelum ini, bila ada perubahan magnetic field, akan ada perubahan magnetic flux. So, berdasarkan equation di atas, kita boleh try to rearrange that equation where cos 0 is equal to 1 and kita bawa A dan juga N, the number of turns of the coil kat depan. So, kita akan dapat dB over dt seperti yang ditunjukkan dalam video ini. Okay, so now the equation for this case, if the magnetic field is changing with time, induced EMF is equal to negative NA dB over dt. Okay, so berdasarkan equation ini, sekiranya perubahan magnetic field itu meningkat, that's mean the delta B, B final minus B initial akan jadi positive value. dB over dt juga akan jadi positive value. Sebab apa? Sebab B meningkat. Maksudnya, B final lebih besar daripada B initial. Jadi, bila delta B, B final minus B initial, kita akan dapat nilai positif. So, when we substitute in the equation of induced EMF above, so kita akan dapat nilai induced EMF is equal to negative value. Okay, jadi sekarang apa maksud negative value tersebut? So, induced EMF is negative because to oppose the increasing in B. Bila B meningkat, nilai induced EMF itu akan jadi negatif, menunjukkan dia sedang oppose the increasing in B. Alright. So bagaimana pula jika case the magnetic field around the coil is reducing? Okay. So nilai B final akan jadi lebih kecil daripada B initial. That's mean the value of the change in magnetic field delta B akan jadi nilai negatif. Jadi bila dB ataupun delta B tadi negatif, we substitute in the equation above. So kita akan dapat nilai induced EMF kita adalah positive value. So induced EMF is positive because to oppose the decreasing in B. B is decreasing, berkurang, and at that time the induced EMF will be positive value. Alright. Jadi bila jawab soalan, pastikan the sign convention of the induced EMF you letak negatif sekiranya jawapan akhirnya ada negatif, menunjukkan the system try to oppose the increasing in B. Okay? Jadi sekarang jom kita beralih pula pada contoh yang kedua. So here let's say the angle is still equal to 0, but this time B and theta is constant. B tidak berubah, angle juga tidak berubah. Kali ini yang berubah adalah dia punya area. So area is changing with time. So kali ini kita ada dA over dt ataupun kita panggil sebagai the rate change of area. Jadi berdasarkan equation, so we can write that induced EMF is equal to negative NB dA over dt. Kali ini B adalah constant, so cos 0 is equal to 1. Jadi dA dt menunjukkan ada perubahan area with time. Alright, so now what happen if the area is increasing? Means that the final area is bigger than the initial area. So delta A, bila A final tolak A initial, mesti akan dapat nilai positif kan? So bila kita substitute dalam equation dekat atas, dA over dt, so dA kita adalah positif, so nilai induced EMF kita nanti jawapannya akan dapat negative sign. So bila jawab, pastikan you letak negative sign pada jawapan akhir awak. So induced EMF is negative because to oppose the increasing in A. Bagaimana pula bila A is decreasing? Delta A akan jadi negatif. Jadi bila kita masukkan nilai dA ataupun delta A dalam equation dekat atas tadi, so nilai induced EMF kita akan dapat positif, menunjukkan induced EMF is positive because to oppose the decreasing in A. Okay, jadi bila A is decreasing, nilai induced EMF kita akan dapat positif. Okey, sekarang kita tengok pula contoh soalan. Jom kita cuba selesaikan example 1 sama-sama. Kita mulakan dengan soalan A. So here we have a coil that having an area of 8 cm squared. Make sure you change the unit to meter squared. And the coil has 50 turns and it lies perpendicular to a magnetic field of 0.2 Tesla. If the magnetic flux density is steadily reduced to 0, means that we have a change of magnetic field. Magnetic flux density adalah magnetic field and dia bagi tahu dalam masa 0.5 second, magnetic flux density is reduced to 0. So now, let's determine the initial magnetic flux linkage. Remember, magnetic flux nak kira lain tidak sama dengan magnetic flux linkage. Soalan bukan tanya initial magnetic flux, tetapi soalan tanya initial magnetic flux linkage. Alright, so now, let's try to answer the question. So before we start, make sure you take out all the informations given in this question. Kita ada A, tukarkan kepada meter squared. Kita ada N, kita ada initial B. So initial B is 0.2 and then the final B is 0 Tesla. Okay, so dekat sini pada jawapan nombor 1, okay, betulkan dekat situ sepatutnya adalah Phi I. Okay, F itu you gantikan dengan I. Saya tersilap tulis sikit dekat situ because this is initial magnetic flux. So initial magnetic flux BA cos theta. So B kita boleh masukkan nilainya adalah 0.2 Tesla. Initial magnetic field 0.2 Tesla and the area is 8 times 10 power of negative 4. So tekan kalkulator elok-elok. So you akan dapat initial magnetic flux is equal to 1.6 times 10 power of negative 4 Weber. Alright, tapi soalan tak tanya magnetic flux, soalan tanya initial magnetic flux linkage. Jadi you perlu darabkan dengan capital N iaitu the number of turns. And finally, the answer for question A1 is equal to 8 times 10 power of negative 3 Weber. Alright, so now for question A2, determine the induced EMF. So, based on Faraday's law, when there is a change of the magnetic flux with time, so there is an induced EMF in a coil. So, macam mana boleh ada perubahan magnetic flux untuk soalan ini? Sebab ada perubahan magnetic field, dB over dt. Jadi, A tadi kita bawa ke depan iaitu area constant. And then kita substitutekan nilai dB, the change of the magnetic field, final minus initial. So final magnetic field is equal to 0 and initial magnetic field is equal to 0.2. So gantikan dalam equation and finally you akan dapat nilai induced EMF adalah positif 1.6 times 10 power of negative 2 volt. Jadi, untuk kes soalan ini, bila B, magnetic field is decreasing daripada 0.2 Tesla ke 0 Tesla, kita akan dapat nilai induced EMF kita adalah positif. Induced EMF positif because to oppose the decreasing in B. Okay? Alright. So now, let's move to the second part. Still example number 1, but question B. So, let's read the question first. A narrow coil of 10 turns and diameter of 4 cm is placed perpendicular to a uniform magnetic field of 1.2 Tesla. After 0.25 seconds, the diameter of the coil is increased to 5.3 cm. So, bila ada perubahan diameter, means that akan ada perubahan area with time, dA over dt. So, question yang pertama, B1, calculate the change in the area of the coil. So, we want to calculate delta A, means that A final minus A initial. Ingat ya, equation untuk area pi r squared, tapi kita tak ada radius dekat sini. Soalan bagi kita diameter, jadi r is equal to d over 2, perlu bahagi 2 diameter tadi dan jangan tertinggal pi r squared. So d over 2 tadi akan kita squaredkan keseluruhannya seperti yang ditunjukkan dalam video kali ini. Kerana apa? Ramai sangat pelajar yang tersilap ataupun membuat mistake ketika mengira area sebab dia terlupa pi d squared over 4. Okay, nanti bila you squaredkan d over 2, ada yang tulis pi d squared over 2. So, bukan ya. A is equal to pi d squared over 4 ataupun A is equal to pi r squared. Jadi sekarang kita boleh substitute terus. So A final kita dah tahu tadi soalan kata diameter dia increase to 5.3 cm. So make sure you substitute betul-betul. So you akan dapat nilai yang betul. So final answer for delta A is equal to 9.5 times 10 power of negative 4 meter squared. Alright, so question B2, if the coil has a resistance of 2.4 ohm, determine the induced current in the coil. So we want to determine the induced current. So based on Ohm's law, we can use that V is equal to IR. Ataupun kali ini kita gantikanlah induced EMF is equal to I, the induced current, times the R, the resistance of the coil, which is 2.4 ohm. Jadi untuk jawab soalan ini, kita nak cari induced current. Tetapi kita belum ada lagi nilai induced EMF. So by using Faraday's law, we use EMF is equal to negative NB B is constant. This time dA over dt. We have a change of area with time. So gantikan nilai dA over dt. Okay, yang kita dah kira dekat atas tadi hanya change of area. So kita hanya kira dA, bukan dA over dt. Kita belum lagi bahagi dengan masa. Okay, so dA yang kita kira dekat bahagian atas tadi adalah 9.5 times 10 power of negative 4. We can straightly substitute in the second question. Tetapi jangan lupa ya, dt, the change of time is equal to 0.25. Kerana apa? Kerana diameter itu berubah dalam masa 0.25 seconds. Okay? Jadi bila ada peningkatan diameter, alright, so means that there is an increasing in the area. So when we calculate the induced EMF, final answer you akan dapat negative 4.56 times 10 power of negative 3 volt. Okay, so pastikan you tulis betul-betul dan jawapan tu you tekan betul-betul dah calculator, and then negatif jangan tertinggal. So negatif mesti letak untuk menunjukkan induced EMF is opposed the increasing in area A. Okay, jadi sekarang kita bolehlah kira induced current, where induced current is equal to induced EMF over R, and final answer akan dapat 1.9 times 10 power of negative 2 ampere. Okay, so untuk induced current, you boleh saja tinggalkan jawapan dalam positive value. Alright, so we finished the first part about non-rotating coil. So I will try to move to the second part, which is still about coil, but this time we have rotating coil. Coil yang sedang berpusing. Okay, so berdasarkan gambar raja ini, kita ada magnetic bar and we have north and south pole, and the direction of the magnetic field must be come out from the north pole of the magnet. Okay, so dalam gambar raja ini kita nampak direction of the magnetic field is to the right, and then dekat situ kita ada a plane of coil, and this coil is rotating around the magnetic field B. Okay, so kita boleh nampak lah ada masa coil ini perpendicular to the field, dan ada masa bila dia berpusing, coil ini akan berada pada kedudukan parallel to the field. Okay, so bila ada perubahan angle sebegini, bila dia berpusing, means that akan ada perubahan angle. Bila ada perubahan angle, akan ada the change of the magnetic flux dphi over dt. So, macam biasa, based on the Faraday's law, bila ada change of the magnetic flux dphi over dt, so kita boleh kira the induced EMF in a coil. Alright, so now let's try to rearrange that equation. So, induced EMF is equal to negative N d BA cos theta over dt. Kita gantikan magnetic flux dengan equation BA cos theta. Dan untuk case yang kedua ini, kita kata tadi ada perubahan apa? Yes, ada perubahan angle. So, magnetic field and area BA dan juga the number of turns of a coil will be constant. So, kita bawa ke depan. So, now kita ada d cos theta over dt. We have rotating coil, means that we have a change of angle between B and A with time dt. Alright, so cos theta is the change in angle. So, since we differentiate respect to time, so we can change that the angular displacement theta, kita juga boleh tulis sebagai theta equal to omega t. Kita boleh gantikan dalam equation kita, dan kita akan dapat kat sini induced EMF is equal to negative NBA d cos omega t over dt. Jadi sekarang kita bolehlah differentiate cos omega t. So ingat ya, differentiate cos akan dapat negative omega sin omega t. Jadi akhir sekali, untuk menjawab soalan induced EMF in a rotating coil, we will use this equation EMF equal to NBA omega sin omega t in order to calculate the value of the induced EMF. Okay? Jadi sekarang jom kita proceed untuk jawab example yang kedua. So I have the first question. A 25 turns circular coil of wire has a diameter of 1.0 meter and it is placed with its axis along the direction of Earth magnetic field and it is given 50 microtesla, and then in 0.2 second, it is flipped 180 degree. Maknanya dia ada putaran. Okay, dia rotate. So sekarang soalan tanya kita, an average EMF of what magnitude is generated in the coil. So bila dia flip 180 degree tadi, maka mana untuk kita kira the average EMF of the coil. Okay, so macam biasa kita guna balik formula tadi, kita ada NBA di cos theta over dt, dan disebabkan kita ada nilai angle, okay, initial angle is equal to 0 and the final angle after the coil flip 180 degree, so kita gantikanlah cos theta final minus cos theta initial, so theta final should be 180 degree, theta initial is equal to 0. Okay, bila kita substitute, kita akan dapat nilai d cos theta over dt is equal to negative 10. Untuk soalan 2A ini, perhatikan betul-betul. Kenapa madam tak guna equation EMF equal to NBA omega sin omega t? Sebab soalan bagi angle. Soalan tak bagi angular frequency omega. Okay, so kita boleh terus cari d cos theta over dt and it is equal to negative 10. So when we substitute all the values in that equation, finally we have answer for induced EMF in the coil is equal to 9.81 times 10 power of negative 3 volt. Boleh? So very simple, right? So let's move to the second part, which is B. So here we have a rectangular coil of 100 turns, has a dimension of 10 cm times 15 cm. So this coil is rotating at a constant angular velocity. So it is given here, and the magnetic field of flux density also given 5.0 Tesla. So let's calculate the maximum EMF produced by the coil. Okay, so kali ini kita ada nilai angular velocity where it is equal to 200 revolution per minute. Nilai yang diberikan itu 200 revolution per minute. So itu adalah nilai omega. Okay, so bila soalan minta kita kira maximum EMF produced by the coil, means that the value of sin omega t should be equal to 1. Okay, maximum value untuk sin adalah 1. Sin omega t must be equal to 1. So, kita boleh teruskan untuk menjawab soalan ini. Kita keluarkan semua maklumat. Omega is equal to 200 revolution per minute. Pastikan bila unit angular velocity revolution per minute, you need to change to radian per second first. So, omega 200 revolution per minute times 2 pi over 60 seconds. So finally, omega is equal to 20.94 radian per second. Area pun samalah. Dimension diberikan dalam unit sentimeter. Make sure bila you kira area, pastikan semuanya dalam unit meter. Okay, so bila kita dah ada area, kita dah ada nilai omega, so we can straightly substitute in equation induced EMF equal to NBA omega. So final answer for maximum EMF produced is equal to 157.1 volt. Okay, so now let's move to the second question. Calculate the induced EMF at the instant when the plane of the coil makes an angle of 38 degree to the magnetic field. Okay, perhatikan betul-betul 38 degree adalah angle antara plane of the coil and the magnetic field, bukan angle antara A dan B. Alright, so untuk angle yang berwarna biru itu adalah angle antara plane of the coil and the magnetic field, which is equal to 38 degree. Boleh? Jadi sebelum kita proceed, pastikan lukis dulu vector of area A, that is normal to the plane. Angle yang berwarna hijau pula barulah angle antara B and A, and the value of this angle is equal to 52 degree. So sekarang bila kita dah dapat nilai angle yang betul, barulah kita boleh jawab soalan ini by using this equation of induced EMF equal to NBA omega sin omega T. Jangan lupa ya, omega T is equal to theta. So kita boleh tulis jugalah induced EMF is equal to NBA omega sin theta, where theta is also the angle between B and A. Sebab kita dah ada angle, kita boleh saja terus masukkan sin 52, and the final answer of the induced EMF for the second question is equal to 123.84. Okey, sekarang kita dah selesai menjawab dua soalan berkaitan dengan rotating coil. Kali ini kita akan teruskan lagi discussion kita berkenaan dengan kes yang terakhir, iaitu induced EMF in a straight conductor. Okey, sekarang tengok dekat sini. Yang pertama, apa yang penting untuk straight conductor, kita mesti tahu bagaimana untuk kita calculate the induced EMF macam yang kita buat sebelum ini untuk kes yang pertama dan kes yang kedua. Dan poin yang penting untuk kita tahu untuk straight conductor juga, kita mesti tahu tentukan direction of the induced current in the conductor. Okay, so jom kita mulakan. Sekarang kita akan lukis dulu. Let's say here we have a magnetic field where the direction of the magnetic field is into the page as shown in this figure. And then kita ada pula satu conductor where the length of the conductor is from Q to P. Panjang conductor tersebut adalah L. Alright, so now let's say we place the straight conductor in the magnetic field B. So kita nampak dekat sini, kita letaklah conductor tu dekat sini. Alright, point number 1. Let's say conductor PQ move perpendicularly with velocity V across a uniform magnetic field B. Okay, maknanya conductor PQ ini dia akan bergerak secara berserenjang dengan magnetic field B tadi. Ingat ya, direction of the magnetic field tadi adalah into the page, and let's say conductor PQ bergerak perpendicular to B, sama ada ke kiri atau ke kanan. Okay, so let's say dia bergerak sejauh X seperti yang ditunjukkan dalam rajah ini, and it is moving to the right, so means that the direction of the velocity V must be pointing to the right. Okay, sebab dia bergerak ke kanan. And then what happens? So second point, when the conductor moves through a distance X in time T. Dalam satu masa T, conductor tadi bergerak sejauh distance of X. So we can calculate the area swept out by the conductor A is equal to L, which is the length of the conductor, times X, which is the distance traveled by the conductor. And then, because of the motion of the conductor is perpendicular to B, so the magnetic flux cutting by the conductor can be calculated by using equation BA cos theta. Alright, so macam biasalah, angle theta is equal to 0 because angle is between area and B. The angle is equal to 0, which is the angle between B and A. So now when we substitute nilai A equal to Lx, so kita boleh tulislah according to the Faraday's law, induced EMF is equal to d phi over dt. So kita gantikan equation BA cos theta tadi, cos 0 is equal to 1, A is equal to Lx. So d over dt BLX. So we try to rearrange. So B and L is constant. Yang berubah adalah dx over dt. Distance with time, where dx over dt is actually equal to V, iaitu velocity. And therefore, untuk kes yang ketiga ini, bila kita nak kira induced EMF, kita boleh guna formula BLV sin theta hanya untuk soalan berkaitan dengan induced EMF in a straight conductor when the conductor move perpendicularly with velocity V across a uniform magnetic field B seperti yang telah kita discusskan dalam contoh ini. Dan jangan lupa ya, angle angle dekat sini adalah angle between B and V. So, seperti yang kita tengok dekat sini, direction of B is into the page and direction of V is to the right. So, angle between B and V is actually 90 degree. So, sin 90, dia akan jadi 1. Okay? So, now let's move to the next part. How to determine the direction of induced current. Macam mana ya nak tentukan direction of induced current? Kali ini kita akan guna Fleming's right hand rule in order to determine the direction of induced current in a straight conductor case. So now let's take out your right hand. So your thumb should be pointing upward and your pointing finger should be 90 degree with your thumb, and make sure your middle finger or your second finger is 90 degree to your index finger ataupun first finger. Okay? So your thumb, okay, cara kita nak ingat thumb, kita ada M. So means that thumb is the motion. Okay, merujuk kepada motion ataupun thumb ini dia mewakili pergerakan. Pergerakan itu merujuk kepada arah V. Okay, and then your first finger ataupun jari telunjuk awak, okay, must be pointing to the direction of the magnetic field. F first, field. F first, field. Okay, so if the field is into the page, so you punya jari telunjuk or your index finger ataupun first finger tadi perlu pointing into the page. Okay, and then your second finger, second, C, okay, means that it's pointing to C is current, induced current. Okay, so kita ada highlight untuk cara you ingat lah. Okay, VBI, V is for your thumb, direction of V, and B is your index finger, iaitu jari telunjuk, and the last one, your middle finger should be represents the direction of the induced current. Okay, jadi untuk contoh tadi, jom kita cuba. What is the direction of the induced current for this example? So, since the conductor is moving to the right, means that your thumb should be pointing to the right. So, V to the right, and your index finger ataupun first finger should be pointing into the page. Okay, sebab itu mewakili magnetic field B. Okay, and then your middle finger ataupun second finger automatically dia akan pointing upward. So, bila dia pointing upward, so means that your second finger represents the direction of the induced current. So, for this example, the answer for direction of induced current through the conductor is from Q to P, ataupun kita kata direction of induced current in the conductor is upward. Boleh? Okey, saya rasa cukup sampai di sini sahaja. Saya ingatkan untuk awak jangan lupa untuk tengok video yang saya tunjukkan ini juga ya, untuk soalan-soalan yang lain. Dan untuk video sesi lepas ada 2 bahagian, video untuk chapter 5 under electromagnetic induction. Jangan lupa untuk tengok. Jumpa lagi. Assalamualaikum. Bye-bye.